The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
An amide is actually a strong resonance donor and is only weakly inductive, and hence it reduces the electrophilicity of the carbonyl group. So it just so happens that the strongest resonance effect happens in amides, which is what makes them very unreactive. So what happens in this case is that this pair of electrons on the nitrogen atom right there can actually be delocalized, resulting in the creation of a double bond right there between the carbon and the oxygen. So there is a substantial degree of double bond character between the carbon and the nitrogen because of resonance delocalization. Okay, so what happens in this case is that we have our nitrogen atom donating electrons through resonance. And as you can see, that pair of electrons right there is being delocalized into the system, resulting in the creation of a double bond between the carbon and the nitrogen and a negative charge of that oxygen right there. Now, on the flip side, as far as induction is concerned, the nitrogen atom is not very electronegative, so it doesn't pull electron density away from the carbon that effectively. So the net effect that we have in the case of amides is that you have a very powerful resonance effect in that the nitrogen atom is donating electron density to our reaction center, our carbonyl carbon right there, but it's not pulling electrons away very efficiently through induction. So resonance stabilization is high and inductive destabilization is low. So that is the reason why amides are very, very unreactive, because the resonance delocalization of electrons makes amides very, very stable and unreactive compounds. Now, esters, on the other hand, also do experience some degree of resonance stabilization in that we can see a pair of electrons from this oxygen atom being delocalized into that pi system, into that conjugated system, resulting in the creation of another resonance contributor that you can see right here. Now, it just so happens that the resonance effect is not as important in esters as it is in amides. So what's going to happen in this case is that although esters do have somewhat of a resonance effect, reducing the reactivity of the carbonyl group, that effect is somewhat overcome by the inductive electron withdrawal that also occurs as a result of the electronegativity of the oxygen group. So resonance is not that much of a problem for esters as far as their reactivity is concerned, and which is why esters will be more reactive than amides, but less reactive than acid chlorides. So they'll be more reactive than amides and less reactive than acid chlorides or acid anhydrides. So that's pretty much what I want to point out in this slide, is that resonance stabilization actually overrides electron withdrawal through induction in the case of esters and amides, which makes them less electrophilic than acid chlorides and acid anhydrides. So I hope that you are understanding what we're talking about in this case. So we have two competing effects. You have resonance, which decreases the reactivity of a compound, and then you have induction, which increases the reactivity of an acid derivative. Resonance is most powerful in the case of amides, which is why they're least reactive, and it's least powerful in the case of acid chlorides, which is why they're most reactive. The inductive effect is most powerful in acid chlorides, which is why they're most reactive, and it's least reactive in the case of amides, which is why amides are least reactive. And that's why we observe the trend moving from an acyl halide, an acid chloride, down to an anhydride, down all the way to an amide. So that is the rationale behind that order of reactivity as far as electronic effects are concerned. Okay, so I hope you've completely understood what we've talked about. I know it's a lot to take in, Just, sit there, internalize these concepts, and the take-home message in this case is that resonance will decrease reactivity, okay, by electron delocalization, and induction will actually increase reactivity by inductive electron withdrawal, right? So the degree to which those two forces are operating in each of these derivatives is what determines their overall rate of reaction.